Okay, in today's video, as you can see, I'm going to go over an explanation for charging a capacitor in a simple RC circuit. And what I want to do in this video is go over three things: how we calculate the voltage across the capacitor with respect to time, how we calculate the current through the circuit with respect to time, and also to give you a good conceptual understanding about what the time constant is, tau equals R times C. And we're going to do that using these two graphs, and this is for charging a capacitor. This graph is a graph of the voltage across the capacitor with respect to time. This graph is a graph of the current through the circuit with respect to time. Now, you should notice here, first of all, that the time in each case for the voltage and for the current is not expressed in minutes or seconds or some absolute time. It's simply expressed in time constants. 1, 2, 3, 4, 5 time constants. 1, 2, 3, 4, 5 time constants. The voltage is not expressed as volts in the sense that 1, 2, 3, 4, 5 volts. It is expressed as a percentage of the maximum voltage across the capacitor. The current is expressed as a percentage of the initial maximum current through the circuit. Okay, so the time is in time constants, and the voltage and the current are in percentages. Now, this is the equation we use to calculate the voltage across the capacitor with respect to time. The voltage with respect to time is equal to the voltage of the battery times 1 minus E raised to the power of minus T over RC. This is the voltage of the battery. This is E. It's a mathematical constant. It's 2.72 or 2.718, depending on how you round. This is T, as in the voltage with respect to time. And this is the resistance of the resistor and the capacitance of the capacitor. And we have a similar equation for the current with respect to time. It's the initial maximum current times E raised to the power of minus T over RC. Now, what is this RC? This RC, this is our time constant. The time constant is calculated as, tau is a symbol for time constant, R times C, the resistance of the resistor, times the capacitance of the capacitor. Now, you should notice, because that each of these graphs is in time constants, that for any combination of resistor and capacitor, any pair of resistor and capacitor, after one time constant, the voltage across the capacitor will always be 63.2% of the maximum. For two time constants, it's 86.5. For three, it's 95. For four time constants, it's 98.2. And after five time constants, when we consider the capacitor to be fully charged, the voltage across the capacitor is 99.3% of the maximum voltage, which is the voltage of the battery. This is an exponentially increasing curve. Now, for the current, it's basically the same thing, except the current is decreasing. After one time constant, the current through the circuit is 36.8% of the maximum. 2, it's 13.5. 3, it's 5. 4, it's 1.8. And 5 time constants, 0.7%. That goes for any combination of resistor and capacitor, because this graph is expressed in time and time constants and percents for the voltage and the current. Now, if we have a case, for example, where we have a 10K ohm resistor and a 470 microfarad capacitor, then the time constant for this pair of resistor and capacitor would be 4.7 seconds. So then we'd look at our graph and we can say all that stuff, one time constant, 4.7 seconds, 63.2%. Two time constants, three time constants, I think that's 14.1 seconds. The capacitor will be 95% charged. After two time constants, 9.4 seconds, the current through the circuit will be 13.5% of the initial maximum. Now that's only for this pair of capacitor and resistor. If we change the capacitor and the resistor, then obviously we get a different time constant. You can see the time constant gives us or tells us how long it takes for the capacitor to charge. That's really what the time constant tells us. If we want to change the time it takes for the capacitor to charge, then usually we change the resistor. Okay? So that is what the time constant is. Now let's look a little bit more closely at the voltage. Okay? So again, we're charging. This is the graph of the voltage with respect to time. This is the equation that we're going to use. Now, this is the voltage of the battery minus 1 minus e raised to the power of t over RC. Now let's just look at what that looks like for one time constant. Okay, a time constant is 4.7. We want to look at for one time constant and calculate the voltage across the capacitor. Then we also have to put in 4.7 seconds here because that's the amount of time, and 4.7 is one time constant. So that ends up being V times 1 minus e raised to the power of minus 4.7 over 4.7, and that gives us V times 1 minus e to the minus 1 for one time constant. Now if we calculate this term, then you'll notice that that tells us that the voltage across the capacitor after one time constant is 0.632 times the voltage of the battery, or 63.2% of the battery. And that's what we have right here. Now for two time constants, I would simply substitute in here 9.4, or simply e to the minus 2. That results in 86.5% of the battery. That's what we have on our graph again. We do the same thing for 3 time constants, for 4 time constants, and 5 time constants. We usually stop there because after 5 time constants, that's when we consider the capacitor to be fully charged. It's 99.3% of the voltage of the battery. Now we can do the same thing for the current. The current is decreasing, so we have one time constant is 4.7 seconds. The time constant is 4.7 seconds, so it's the maximum times e raised to the power of minus 1, and we end up with the current is 36.8% of the maximum. If we substitute 2 time constants, 13.5%. 3 time constants, 5%. 4 time constants, 1.8. And finally, when the capacitor is fully charged, the current through the circuit is 0.7% or 0.7% of the initial maximum current. Okay? So that's how the voltage and the current equations work, and that's what the time constant is. Now we can summarize that with this table. This is the time constants 1 through 5. This is the voltage expressed as a percent of the maximum. This is a current as expressed as a percentage of the maximum. And these are the values that we got for the increasing voltage and the decreasing current. You'll notice if we add these two values up, they add up to 100%. Sometimes we want to know when is the voltage across the capacitor 50% of the maximum, and when is the current reduced by 50%. That occurs at just about 0.7 time constants. Okay? So there you go. I hope you found that video helpful. I tried to do all three of those things, show you how we calculate the voltage across the capacitor with respect to time, show you how we calculate the current through the circuit with respect to time, and then also to give you kind of an understanding what the time constant is. So thank you very much for watching. I hope you found that video helpful. If you did, please do all the following 3 things. Subscribe to my channel, give me a thumbs up for this video, and leave me a nice positive comment in the comment section below. Thank you very much for watching. We'll see you in the next video.